That is correct.
All right, cool. Let me see if I can get back here. All right, I could get back here. Okay, so this device here, which looks like it's from another planet, this is an actual real-world quantum computer, and we're simply showing that to emphasize something that I think most folks in this room would intuitively know. You know, this isn't a theoretical concept. People are building these. They're building them smaller and smaller, cheaper and cheaper, and pretty soon we'll likely have high-level language integrations into quantum computing. I went through this before, although I should be saying cryptography. It's just natural habit to use the word crypto. So when you hear that, please don't think Bitcoin. And just to kind of emphasize, and I'm going to try not to move around too much. It's in my normal nature to do that when talking. But this is something you can actually go lease or rent. This is a 20 qubit rack-mounted quantum computer. Amazon is kind of testing the waters with some of this, but you can see how this is no longer in academia, military intelligence, and research. This is actually becoming commercial, and that's only going to increase as you know, the state of the art evolves. So what do the traditional algorithms look like? And I'm going to start out really with ciphers, and I'm not going to cover by any means all of cryptography. We definitely wouldn't have time for that. But asymmetric crypto basically involves a public and a private key. You've probably integrated that at some point with JCE, or you know, anytime obviously you're using a web browser, you're taking advantage of that. And the public key can be shared with the universe. The private key has to be very closely guarded. And the prototypical example, and one of the founding examples is RSA. So asymmetric has been around for a very long time. It involves fundamentally math problems that we think are hard for traditional computers or traditional algorithms, whether that's factoring primes or, you know, working with exponents. So the cool thing about asymmetric crypto is that it's not just for encryption and decryption. You can use it to sign and verify messages. You can combine it with itself and with other primitives like message digests / one-way hashes with symmetric crypto to make much more advanced protocols, such as, you know, something like TLS. So the biggest threat that quantum computing poses is actually to asymmetric cryptography, at least in the immediate future. So we'll go into, you know, what are some of those threats, and what would, you know, fall down when that actually happens. I say here at the end that it depends on hard problems. These are hard problems for traditional computers where, you know, the time complexity is just too high for it to be solved in a reasonable amount of time. That isn't the case necessarily with a quantum algorithm. So the quantum doesn't mean magic. You know, there's classes of problems that it can solve, but this happens to be one sweet spot for quantum algorithms to try to crack. On the other side, and actually, I think historically occurring before asymmetric crypto, is symmetric crypto. And instead of having a public and a private key, you just have one symmetric key. The challenge with that is always how do you exchange it? So you know, the two of them have different strengths. The symmetrics are typically orders of magnitude faster and more efficient than you know, the asymmetric algorithms. And AES is probably the de facto standard right now, but an AES is a block cipher. You also have Cha-Cha-20, which you know, is a stream cipher, very, very fast, very, very performant. So that's really the big dividing line in the ciphers, is really how are the keys being used. You either have one that does encryption and decryption, or in asymmetric you have a public-private pair. Now, I'm guessing a lot of folks know this, but they're not apples to apples. So, you know, a 2048-bit RSA key sounds really big. It is pretty big. But, you know, it's significantly weaker than even a 100, or certainly weaker than a 256-bit AES key. Definitely stronger than a 128-bit AES key. So the rule of thumb, and it kind of varies, it's more of a curved graph, but at kind of higher key sizes, it's 10 times weaker, depending which way you're looking at it, and lower sizes, it's about 20 times weaker. So both are great tools, right? We use both in our toolbox. We use the symmetric for the speed and the efficiency and larger messages, but we need some way to exchange the key without putting it under guard and transporting it, or using USB drives like in the old days. Well, probably disks in the older days. So ideally, what you want to do is combine the two into a protocol where you get the best of both worlds, where you use the asymmetric cryptography to then encrypt just the symmetric key, and now you can exchange something that's really small, and that efficiency isn't such a barrier. And now, once both of you have the symmetric key, you're off to the races, and you can, encrypt it and decrypt at high speed. So now I'll, kind of ask, do you know why the hash got stuck at the end of the road? Because it could only go one way. I'll give everyone a chance to digest that joke. So, really, what one way hashes do, it's not encrypting and decrypting. It's really used for authenticating, not identity, but saying, yes, this is the same file, data, etc. that I was expecting to. So you could take a multi-gigabyte file or a huge, petabyte stream, and it's going to produce 160-bit or 512-bit or whatever it is, really small hash. And the cool thing about the one-way hashes is if you change even 1 bit in that multi-gigabyte file, you'll get a completely different hash, or you should get a completely different hash. So some of the examples of one-way hashes that you've probably seen before are MD5. Don't use that anymore. SHA-1, don't use that anymore. SHA-256, which is part of SHA-2, and C-shake or configurable shake is one of the newer ones. The cool thing about C-shake is it actually allows you to alter the size of the output hash. It also allows you to feed, you can think of it as salt into the hash, and even the same data will now hash to different values because they have different salts. So C-shake is pretty cool as a hash function. And the way I always think of this, and most of these are not implemented with modulus, but if I say 22 mod 5, the answer there is 2. But if you only knew the answer, and even if you knew that 5 is being used, there's an infinite number of numbers that could have produced that. So that's why it's called one way. It's really, really hard, if not impossible, to go backward. And then when you're working with hashes, just be aware of what we call the birthday problem, which is, and I'll throw this out for the group to guess, but how many folks would have to be in the room to have a 50% chance of 2 of them having the same birthday?
20, 15, 14,
23. It is 23. I think most folks on the street, if you were to ask them, would say, 365 divided by 2, 180 something, 181 or whatever it is, 182. But no, just because of the probability of collisions, whenever you're looking at a hash, you really have to take that exponent, however many bits that represents, and divide it by 2, because that's the odds that eventually 2 hashes are going to collide. So that's an example of when you look at a hash strength, really divided by 2, because that's the space in which you're at least likelier than not to have a collision. Okay, I think I touched on this just a little bit early. We use what we call cryptographic primitives, the asymmetric, the symmetric, the one-way hashes, and a few others, and we combine them together to create something like a digital signature or like a key exchange protocol. So the cryptographic primitives are really kind of what we're worried quantum computing attacking, because if you get the primitive, you also now, in a relatively straightforward fashion, are able to attack the overall set of protocols that are using it. I think folks are familiar with, key exchange, Diffie-Hellman, elliptic curved Diffie-Hellman key exchange, and then how those, integrate into PKI. A lot of asymmetric crypto being used here. So if you're looking for what do people usually grab out of the toolbox, or what ought they grab or not grab, these are the more common implementations that if you were using JCE that you would want to instantiate. And you can see they start to get a little bit more complex than just saying, oh, I'm using AES, or oh, I'm using SHA-2. So here we're using AES with Galois counter mode, which is the most efficient mode to use it for in most cases, and we're adding authenticated encryption with it, so that ciphertext can't be tampered with or spoofed or replayed, etc. So you'll typically want to take the algorithm and combine it in the right operating mode. And there's an awful lot of resources on the internet to help you out with what are some of those better combinations, what are some of the bad ones, right? Like, we don't want to use CBC in AES if we can help it, right? There's definitely some use cases for it, but that's not what we want to just reach for unless it's something exceptional. Two really good books if you want to dig a little deeper. One is called Practical Cryptography, and that's very much for, hey, I just want to integrate this into my services, my applications, etc. And then there's a book by the inventor of SHA-3, Amundsen, I think I'm probably mispronouncing his name. And that's a kind of a step up where you don't necessarily want to learn the hardcore math, but you really want to know what are the pitfalls and what are the best practices. Like, when do I have to reseed entropy in my secure random, and considerations like that. All right, we're now leaving the land of the traditional, which I think most of us are familiar with, and starting to think about, well, what's on the horizon? Why are we really worried about this, and how worried should we be? So Shor's algorithm, which I think came out in 94, 95, something like that, really allows for front-on attacks for asymmetric cryptography. So rather than being an ON problem now to attack a given cipher, it's O square root of n. So let's say you've got something that's 128-bit strength. Notionally, Shor's algorithm is going to take that down to 64-bit. And now you're starting to talk about something that, oh, maybe that's, I'm sorry, that's Grover's. I skipped ahead. Grover's is attacking symmetric. So, most folks here are probably using AES 128 somewhere. That means that AES 128 is now AES 64. And if you're using 256-bit, now it's 128. So once quantum computers are able in the next few years to actually run this algorithm, say with 100 qubits, something on that order, people are going to start to get worried about the safety of those symmetric ciphers as well as the asymmetric ones. So as we showed before, those computers exist. You can rent a 20 qubit one right now, so it's probably only a few years away from renting higher and higher qubit machines that make these algorithms feasible. And if that's what the commercial state of the art is, nobody really knows what the NSA or government actors like China or criminal syndicates are using, but they're certainly higher than 20 qubits. Just like Frank indicated in his intro, due to the cost of storage, people are just grabbing ciphertext right now and storing it, thinking, well, I can't read it now, but maybe in 5 years I will be able to, and maybe it's still going to be valuable. So I think whenever you're looking at your data security, what kind of adversary are you expecting? And obviously, the greater the sophistication, the higher the security you're going to want to put on that. How long does the data actually have to stay safe, right? Is this just a web session and it might not, have a very long duration, be fairly transient, versus a little trivia. What is the type of data that requires the highest security in the US government? Well, for me, it was a surprising answer. It's the US Census, because by law, that data has to stay private for 70 years. So they actually have to encrypt data that's going to stay safe with all of that, PII and what have you for 70-year time horizon. So somewhere between a web session and US Census, level encryption, is probably your use case. And nobody really knows, how long it's going to take. But I put this graph up, and this is from several years ago. We hadn't even crossed the quantum supremacy line. I think this was from 2016 or 17, and Google hit it in 2019. And I think the definition there was somewhere around 50 or 60 qubits. But a few years ago there was a big declaration by Google that we've achieved quantum supremacy. So it's not theoretical anymore. It's something that will happen. We're just not sure when. But every time we've had an estimate of when it would happen, it's come earlier, like so many other things in technology. So what are you looking for in a post-quantum cipher? And I'll use that term. So right now in traditional algorithms, most folks, would be using something around 128-bit AES, cha-cha, something like that on a symmetric cipher for data in transit or data that doesn't have to stay secure for very long. And then for data at rest with a traditional algorithm, you'd want 256. But as we saw, chop all those numbers in half when even a simplistic quantum algorithm is attacking them. So our recommendation is to go to 512-bit if you can, and those particular ciphers won't go that high. Most of the post-quantum ciphers are started at least 256 and definitely are going to 512 and potentially higher. So and to just put it into perspective how strong 512-bit is, your odds of winning 18 Powerballs in a row and then being hit by lightning is the odds of guessing one of those keys. So that helped put it in a better perspective for me. And then those numbers are significantly higher than even all the atoms that exist in the universe. So I know that's base 10 instead of base 2, but it's significantly lower than 2 to the 128. So that's really how strong this is, and it's kind of amazing to just think how many permutations that is. I was at RSA a few weeks ago and actually got to play with a real Enigma machine with someone from the NSA watching behind me as I was typing things in, and that thing had a few million combinations, and it was still almost unbreakable for the longest time during the war. So it's pretty amazing just to see how much larger key sizes have gotten, and yet the cryptography is still extremely performant. Now, speaking of performance, what you'll typically see in a normal cryptography algorithm is as you increase the key size, you get worse than linear ON performance. You'll get something ON squared, sometimes even worse. And that's why there's always been this traditional trade-off between are we going to be more secure or going to be more performant. The next generation of ciphers, the ones that are going to try to do 512 and higher, they have to at least be ON or better. So that typically involves different types of math and different ways of doing the encryption. And then if you're operating in like a financial trading environment, or if you're operating in a critical industry like nuclear power or an electrical industry, there's actual requirements that whatever you're putting on one of those wires can't add more than a certain amount of latency. So if you're looking for something that's truly performant, look for something that's Goose certified, which states hey, this is 5 milliseconds or less, even in a worst case. That's our favorite big O complexity graph. I just threw that in there because I always like looking at it. So I'm not an actual cryptographer or a cryptanalyst. I think of myself as a cryptography practitioner. You know, I take things that people use and then try to you know, solve problems with those. But even that is hard. You can make a lot of mistakes. You know, you could have a non-unique nonce. You could have a weak initialization vector. You could pick a bad padding scheme or a bad operating mode, right? And the algorithm is still the algorithm. So even just using a lot of you know, these tools, you can make easy mistakes. So what I would say is at least read Practical Cryptography when you have a chance. It really goes through you know, what should you do, what shouldn't you do, and it's very, very much for the, you know, developer focused kind of audience, not for the cryptanalysts and the mathematicians. But developing new crypto is even harder, right? You've got to look for something that other cryptanalysts trust and peer reviewed. If you go to the NIST government website, there's a whole series of approved post-quantum algorithms that you can pick from and kind of play with, and I'll put a list of some of those up there. One little caveat: nobody really knows if they're quantum resistant, right? Because you know, we just think, okay, bigger key, stronger, harder problem. But you know, someone could always invent another mousetrap, a new kind of math or a new way of using qubits that nobody has thought of. You know, Shor and Grover came up with two algorithms, and a lot of people are going to come up with even more novel algorithms. So the, you know, it's with a little asterisk that, you know, based on what we know today, it seems like, you know, those should be okay. But, you know, caveat emptor. And then one last thing that folks might want to start thinking about, you know, you can just go use Java random and get a random number, but, you know, that's not cryptographically secure. You could take a step up and use secure random, you know, which is more secure, but even and cryptographically strong. But you really want to initialize that with something that has actual true randomness instead of pseudo randomness. So maybe look at there's now quantum entropy providers like Quantropy and Quantinuum and several other firms. I think Quintessence Labs does it too, where they'll actually, you know, use lava lamps or radioactive decay or entangled whatever, and they'll give you actual, you know, quantum randomness, and you can even, you know, buy whole, you know, gigabytes of just these were totally randomly, verifiably randomly generated numbers. So kind of start thinking, and obviously there's hardware tokens, there's all kinds of other things you can use, but you know, just reaching for you know, Java random is not going to be secure. Secure random is better, but really start thinking about how you're handling and generating your entropy, because it's a key ingredient to all of cryptography. If you have bad entropy, you know, even a good algorithm is not going to save you. All right, I'm putting this up here. Has anyone ever heard of the perfect cipher? Like aliens with 1 billion years more advanced technology than us wouldn't be able to break it. Actually, provably unbreakable. So this was developed in its 1950s, 1960s technology, believe it or not. What you do is you take a source of actual pure randomness, like a lotto ball spinner, and you pull a number out, you write it down in a book, you write it down in a copy of the book, and then you put the ball back. You have to put the ball back. And then you just keep doing that. And what ends up happening is you have a source of pure randomness and some message. There is no math, there is no quantum calculation that can unscramble it, because, you know, you put something in that was truly, truly random. Now, the use case for this, where they've done this, was the old US Soviet Union red phone. And in that kind of a situation, you know, you can afford for an army to go take a copy of that book under military guard and bring it over to the Kremlin, or I don't know which way they went. And then people can, you know, totally securely transfer their messages. It's called a one-time pad. So given that one-time pads are super expensive for everything except, you know, preventing nuclear war, you know, we need to do something else. And you know, a random number generator is something that is actually random. So like on a Unix or Linux system, it's looking at, you know, what is the boot time, what's the temperature, how are the keystrokes, and it's trying to just collect as much entropy as it can. And that's why it's expensive, right? You know, the rate at which it accumulates and you know, entropy is very, very low. So what we combine that with are pseudo random number generators like secure random. So those are deterministic. You supply the seed, ideally something that's really random, and then it'll deterministically go. And that's why I was bringing up the birthday problem earlier. For example, I think secure random by default uses a hash at the end of the day that creates a total seed space of like 128 bits. Well, because of the birthday problem, that's only 64 bits. And now you're starting to think, well, somebody could just try all those combinations. And in fact, you know, hack your pseudo random number generator. So that's kind of the state of the art where it is with randomness until QRNG came around, and those are actual, you know, quantum generators generating randomness. And typically, they're never going to be as fast as, you know, something running an algorithm on a machine, but they can generate, you know, decent amounts of true randomness much more reliably and much faster than just an RNG running on your machine. So this is kind of the famous example, right? You know, shining a light through a lava lamp and, you know, just recording how it changes. That's a great way to generate entropy. And a few companies actually will have that, you know, in their lobby to show you how they're, you know, generating entropy. Nowadays, this is a non-quantum source of randomness, but, you know, now they do actually use entanglement to generate randomness. So these are some of the current finalists and or recommended implementations. So if you're using a signature, XMSS and Sphinx are actually completely endorsed by NIST and recommended for, you know, for people to use. At least 3 of these top ones are, I think, 3 of the 4 finalists in the most recent competition. But there's kind of an asterisk here because one of the former finalists was broken on a laptop in a few hours on a traditional computer. So even though NIST thought it was fine and they thought it was fine, you know, someone was able to crack it just on a regular laptop in a trivial amount of time. And then Kyber was actually broken with an AI algorithm, which nobody thought someone was going to apply to the problem. So I think Kyber is going back to the drawing board and you know, figuring out what they can do differently. But typically, Kyber and a few of these others, instead of using you know, discrete logarithms or you know, prime factorization, they use what's called lattice-based cryptography, and it's a geometric version of keys, just like elliptic curves are, and it's believed they're going to be quantum resistant, but nobody, you know, nobody really knows. So we'll find out next year. NIST will actually have the post-quantum encryptions standards finalized. I think there's a 2nd or 3rd draft that's out there that just came out a couple of weeks ago. But if you're in the financial services industry, if you're in healthcare, if you're in the military, you know, these are some of the industries that are going to likely be impacted by any mandates that come down, or, you know, at least recommendations that come down first. So if you're in one of those industries, I would, you know, recommend that you pay a little bit more attention to, you know, those kinds of developments. And what are some easy ways to do that? You know, if you're on Reddit, our cryptography is a great place to go. So half the time you're getting kind of students asking questions about how to do something, but the other half of the time you're getting, you know, people talking about cryptography news, which I find a little bit more interesting. And then there's obviously our quantum computing. So, you know, our cryptography will tell you what's your defense, and our quantum computing will let you know, well, what is the offense, you know, doing, and what is their state of the art. So it's a nice low level way just to kind of stay on top of that. And if you're interested in doing or at least simulating quantum computing over in Java, there's actually one of those in action books where you can download the simulator and kind of play with, oh, this is what, if I had qubits on my computer, this is what, you know, they would probably do. So anyone that's interested in that, it might be a fun side project. So I am going to try to share the right screen now and give you guys a couple demos. This is going to be interesting. This will be a video within a Zoom share. So I'm going to start my computer's screen here, so you can see me and hear me in stereo. And right now we've got the encryption at 512-bit, the lowest strength. So again, that's 18 Powerballs in a row and being hit by lightning. And as strong as AES 256 is from unencrypted data, this is that much stronger to 512 because it's exponential. So I'm going to go and encrypt. And if you see, might be slower for people that are streaming, but there's really almost no lag. If you can see the actual times there, it's probably because I'm on battery. But extremely, even at 512 bits, it's having no problem handling video whatsoever. And if, in case you're wondering, oh, is it actually doing anything? I can turn the decryption off. And that's what it would look like if you were sniffing, you know, the wire. And then we can turn the decryption back on. We can go and modulate the strength every 2 seconds. So we're actually completely changing the key size without reinitializing anything. And when we get to kind of the highest strength, you can see it slows down just a little bit, but it's not, you know, it's not significant. So if I stop it here, you know, we're going to increase the strength by 20 and the latency increased by 4 or 5. So this is kind of what you really want to find in, you know, in a post-quantum cipher, because as these key strengths increase, you don't want to see that exponential drop or, you know, increase in latency. You want to see it log n, or ideally, you know, constant time at the worst. So, you know, that's 10,240 bits. That's something that's, you know, just obscenely strong. No one really needs that, but it still, you know, performs relatively well. I might look like an 80s TV show, but you know, it's still video. And if I drop the strength all the way down to 512, you know, there's really no lag whatsoever.
Down to the max, it's basically no more lag because it's running so much pressure on the computer as you get the pictures out, right?
I'm sorry?
If you raise the strength all the way back to the max, you're seeing some minimal lag that's there because he's putting so much pressure just to get the pictures out, right? Yeah,
I mean, the actual CPU doesn't end up getting pegged. Like, you know, like I don't really hear the laptop running even at 512. There's just more work, you know, to do for the encryption and for the decryption. So that's why it's slower, but it didn't get 20 times slower. It only got 5 times slower. So those are kind of the performance characteristics you really want to see in a post-quantum cipher. And that's just I always like the video demo because, you know, you can't fake video. It's either going to come across in sufficient speed, or it's not going to come across in, you know, sufficient speed. And there's also, I'll show folks what the code looks like to run that. But let me go to my downloads folder. All right, and if I want to just do something command line, and maybe, I don't know if this happens to you, but people send me stuff all the time, like on Slack, and then it's work related or sensitive, and I somehow have to get it, you know, over to somewhere that work actually approves. So I do something like this. It's just regular jobs, autocomplete on Windows. So we'll just encrypt that zip file. So that was 512. That was, you know, really fast. That was a 7 meg file. And you can see it's created both a key and then also the encrypted file. And if I tried to unzip that file, you know, it would just be gibberish. I can reverse it. And this time I'll pass it the encrypted file. Oops, that wasn't good. It's my fault. Oh, I don't have a period there. And I've got the same file back. I could have actually erased it and it would come back and I could unzip it for you, but I think a zip file isn't quite as compelling as just seeing something work like on the desktop. So we have a lightweight OS integration. You can see that, or maybe it's harder to see, but there's actually a border around the window now that's green, letting you know that you can encrypt and decrypt things. So if I click this, little crying baby, now it's completely encrypted and can't be viewed by anything. And then if I were to click it again, I can decrypt it and I've got the baby back. So, you know, that's kind of not necessarily for programmers to use, but if, you know, you want something nice and easy and convenient, you know, just to, you know, secure things, that's an easy way to do it. And then I'll try and keep my fingers crossed here to bring the PowerPoint back and show you some of the code that just does that.
It should be fine this time.
Yep, I hope we'll see. My middle name is Murphy today with the get this back up. Get down to where we're. Oh, if anyone wants to play with it, you should have gotten a zip file in an email. You can totally play with that, or you can scan this QR code or type that in. That just downloads like the SDK. The Windows integration we haven't quite released yet. That's like a alpha feature. It should be in beta very, very shortly. And I don't know if Frank, you want to send that out later for people who just want to play with it right on their file system. Believe it or not, the most challenging thing with that is the installer. Those things are really tricky to use. I don't know why. But I'll just show how easy it is to do the encryption. For those of you who are familiar with JCE, it's not, this isn't the JCE wrapper. You simply say, hey, I want to use string-based encryption, file-based encryption is supported, and then stream-based encryption is also supported. So this is basically a singleton, and you just say go encrypt hello world at 12-bit strength. And I'm only doing this once, it's a single job, and I also want you to generate me a key. So that's all it takes to do an encryption. You could specify up to 10,240 bits if you wanted, and all of that is available from the command line. And then remember, we have this encrypted result. We'll just go take that encrypted result and decrypt it. And if you were to actually run this code, it'll print, you know, hello world, maybe not the most interesting thing, but at least a traditional, you know, demonstration. So here we pass in what was the ciphertext, what was the key that was used, and then just go and decrypt. So those are just a few different ways to use it. Certainly not saying, you know, you would have to use ours. It's only one of a few. It is NIST certified. You can go on the website and find it. And I know that's probably important for some of the folks, especially in finance. But if you just want to play with it and see like what does, you know, really, really strong and almost sometimes comically large key sizes, how does it work and how does it perform? You can totally feel free to play with it. And with that, I'm going to open up to any Q&A, and then I'll ask Michael, who's also on the Zoom call. He's actually the author of the crypto, so if there's any lower level questions, I'll probably kick those over. But yeah.
Awesome. I've got a couple of questions.
Sure.
So where I'm coming from is I was in the financial world. Now I have a small startup. We've got a mobile phone app. We submitted to Apple today.
Oh, cool. Congrats.
They haven't.
You might be waiting a few days, but yeah.
That's okay. And the back end is in Java. And I'm not just the back end developer, I'm also the DevOps guy. And you put up a website in the internet before it has a domain name, it's being attacked
Mhm.
within a couple of minutes. And I don't worry about that because they can only try 3, 4, 5 times. And so the quantum computing isn't going to do them any good whatsoever.
Mhm. Well,
Am I wrong?
Can you summarize the question? Yeah.
yeah, I'll repeat the question. So he's saying, got an app out for review. So congrats. And then the back end is also got a traditional back end in his website. He's got attached to that, and he's not as worried about the quantum adversary because they can only try so many times in such an interval, right? So it's not like someone's going to go brute force your site, right? That's basically the.
Well, they're trying to do that constantly.
Yeah, well, I think there's a few potential things to worry about there. One, if, or it's almost certainly when, because Shor's algorithm attacking asymmetric crypto, this is symmetric, but attacking asymmetric crypto, people have very, very high confidence and very, very high worry levels that those are going to be the first things to fall.
I understand, but I mean, the whole idea of quantum is that they're able to try billions of times a second. And
right, so let's say they grab the public part of your certificate and using a variant, right? Because you're just vending that to everyone who's making a TLS connection, right? Yeah. There's some research and some people working on quantum algorithms that given the public portion, they can recover the private, right? So that's just one example. Another one might be that they're just snooping on the traffic, right? And yeah, they can only make so many attacks over the wire so quickly, but now that they have the data, they can brute force it, right, to their heart's content, right? They just have all your ciphertext and now they apply their algorithm to it on whatever machine they want. So there's definitely ways, that it could be worrying if even just for the website, where the rate at which TCP goes is going to limit how fast they can attack you. But whether it's taking something that's public and reversing what is the private part, that would be devastating, right? Then they can impersonate you, they can do whatever they want, or just grabbing as much ciphertext as they can and then decrypting it later when they at their heart's content. There's probably a few other kinds of attacks than that. But yeah, you're right. If someone's just trying to come in the front door, they're not going to use a quantum, algorithm to constantly just be, knocking and see if they get a hit.
can I ask one more question?
Sure.
Sorry.
One more and then I get a chance.
Okay.
And then your turn.
No,
Then he gets a chance. Then we all get a
So
chance.
the next question is totally on the other side of the other spectrum, other than website of blockchain and what everybody else thinks is crypto.
Mhm.
You have an estimate of when that's just going to go away because of this? I mean, from what you're saying.
Mhm. Yeah.
Blockchain, and I mean, has to be what people are going to be attacking quickly.
Oh yeah, absolutely. And
At some point, it's just
Mhm.
Bitcoin is going to go down to zero again.
Yeah, the question was, in putting on my prognosticator hat, which doesn't always fit and isn't all that accurate. When will blockchain fall? And in the time horizon, I think it'll be sooner rather than later because they are using a lot of asymmetric, tools in their toolbox for the blockchain. Symmetric is gonna fall a little bit later in all likelihood, but I would be willing to bet 3 to 7 years, somewhere around that before, and you're not just talking about blockchain, right? Once RSA and these other algorithms start to become vulnerable, PKI becomes vulnerable, right? TLS becomes vulnerable. So it doesn't mean everything is going to be vulnerable, because what these typically do is reduce the problem space, right? Reduce the effective strength that the person thinks they have, but you still then have a relatively hard problem that needs a lot of computing. So I don't think, there's going to be some quantum script kiddie attack anytime soon. You know, this is definitely people that still have resources and will go after high value targets like financial industries, like blockchain, like things like that. Yes.
Okay, so if I'm reading between the lines here, then your expectation is that the National Security Agency or equivalent organization can record an HTTPS session today between any two parties they can man in the middle, which is like everybody in the United States and probably a lot of other places. Save that encrypted session on their storage.
Sure.
And then in 5 years, maybe 10, they can decrypt that HTTPS session, see everything that went back.
Yep. Exactly.
There are no TLS. TLS is just not quantum resistant at all.
Not the current implementation, right? Because
Just repeat the-
sorry. Is it, is the NSA hoovering up data and recording it? And in a few years, will it be able to decrypt it? So a few things that we already know happened. We already know that they had code that was on the internet backbone and was able to actually intercept things before the ISPs could even realize that it was going through. Because they were actually on the backbone, and in just milliseconds of advantage, they were able to reduce the strength of just TLS using traditional attacks. We know they did that. And when well, it's almost certainly hardware that somehow they got on there or broke into the backbone providers and got their code in there, right? There's I'm sure there's lots of different ways that they've done it. Sold machines that had tainted hardware that were then installed in those kinds of locations. So we know all of that was done, and we know that decades ago in 3 deaths there was a theoretical attack that reduced it to 2 deaths, which was now a tractable problem. Revelations came out that the NSA had enough memory and this giant code table that could actually, years before that attack even came out, reduce 3 deaths to 2 deaths. So we know they were doing stuff like that. Snowden had an awful lot of revelations, like releasing elliptic curves that they knew were weaker. And that's why Signal and some of these other companies have come out with their own elliptic curves that aren't, from the NSA. So on the one hand, it's impressive, but on the other hand, I wouldn't put much, past their abilities to do right now. There's almost certainly quantum encryption. We've been talking about, attacks against regular encryption, but actual quantum encryption, say between the NSA and the White House, or I know China has sent quantum encrypted streams back and forth all the way to a satellite and back. So, these nation actors with lots of funding are doing things that the research community isn't even aware of.
Say quantum encryption, do you mean an algorithm or do you mean coupled particles?
Both. An algorithm that takes advantage of true quantum entanglement. So it's an actual quantum encryption. So we know those exist, and I don't know how many tens of miles or hundreds of miles it is between the ground and the satellite, but they're able to do that. At least China is able to do that as well. So all these things are not. They sound like science fiction, but they're actually real. Yeah.
Two-part question. Does quantum encryption provide an advantage against quantum decryption? And if so, is this a race to the bottom? Like, is every company, every single entity going to need a quantum computer to encrypt?
Yeah, I think so. All the question was, are folks working on using quantum encryption and quantum decryption using actual quantum mechanics, entanglement and what have you? And is that just a race, to the bottom? Will we all need quantum, hardware? I think so. I'll take a step back. Everything you saw right now there, aside from the entropy generation, I don't actually have like a quantum token or anything in here, but that's where you see like the commercial space at right now is, okay, well, let's use quantum entropy and then we'll feed it into, it's still running on traditional, computers, but it's a quantum resistant algorithm. So the current kind of state of the art for people that aren't governments and researchers and have quantum hardware is to do something like that, like go purchase right quantum entropy and then plug it into a resistant algorithm, and you kind of get all of the speed and the familiarity of operating on traditional silicon, using von Neumann architectures and everything we're familiar with. But there are actual quantum encryption, tools. And like I alluded to earlier, at some point, and I think it'll be pretty soon, because you can go rent quantum computers that actually operate with real quantum mechanics in a rack right now with 20 qubits, but it's kind of like, working in a very, very, very low level language that's not familiar, so it's the quantum equivalent of assembler. And I think it's only a matter of time before higher level languages, something more akin to C that's a little more friendly and a little more familiar. And then finally, maybe before this decade is out, I bet there's going to be something, if not Java, then something like Java that, it'll be Java X crypto.true, right? And you probably have to think in a different way to program like that. I'm not sure what those true quantum algorithms look like, but they're taking advantage of the qubits, and they have this other. It's not so much that they're necessarily stronger, right? Because that was 10,220, right? I mean, that's more strength than anyone will ever need. It also has this property that if it's intercepted, the communication is instantly destroyed. So you almost have this built-in detection mechanism in a lot of these quantum computers, where if someone tried to man in the middle, you would know, because you're no longer receiving a communication, right? They intercepted the message and you didn't get it. So I think that's the big difference in what I've seen. It's not necessarily that it would be stronger than anything that a traditional computer could do, but it does have this really cool, detection of intrusion just automatically by the way it works. Yes, sir.
Very fundamental question. Over time, when everybody used passwords to mitigate password being compromised, 2FA methodology was introduced.
Mm-hmm.
Now, in terms of cryptography and the power of computing as it increases,
Mm-hmm.
are there any other different approaches that are being considered to say, hey, we know it's an eventuality that this will get broken or compromised.
Mm-hmm.
So we need to take a different view at achieving certain level of secure communication. So in which the design of the approach itself has been modified. Has there been any discussions or dialogues around this?
So let me see if I got so at a high level, you were asking if there are different approaches that are going to be used for security, but you started everything off with passwords. So I was trying to figure out where.
It's like passwords are there, and then it can be broken. So how do we generate a randomness in it?
Mm-hmm.
So it's like, okay, password can be broken. We are changing the approach, saying that we will not depend on the randomness, which is always a constant
Mm-hmm.
in some ways, and it can be broken. So it's a variable value, right? So it is like achieving security via a random value introduction real time.
Yeah.
So the device here, it seems to me, is that encryption will, as the computing powers increase, certain levels of encryption will be easily broken.
Mm-hmm.
So the possible mitigation is use a longer key, but again, there are limitations to it. So is there a different approach that can be taken so that we achieve the goal of not as such real-time encryption of communication,
Mm-hmm.
but making it the key harder itself, because there are multiple factors involved in that generation.
So the question is, how do we improve security without simply lengthening keys as we move forward? And I would say, lengthening the keys is mathematically very, very effective. And if the algorithm is still performing at the larger key size, it's assuming you're getting the latency that you want. That to me is a really easy winning strategy, right? Because none of these magically just find the answer, right? They reduce the problem space. So if you increase the problem space more than they can reduce it, you're still ahead. So, that's something to always keep in mind, that at the end of the day, the strength is in the key, Kirchhoff's principle, one of those bedrock principles of cryptography. So I don't think it's necessarily bad if you're increasing the key size. That's logical. It's only bad if you doubled the key size and now you have 8 times worse the performance, right? That makes you want to not double the key. But when you get O log n performance when you double the key, why not do it, right? Yeah, you're paying a slight hit, but it's less than the value that you got out of, doubling the key length. And I think, in the farther future, people are looking at things, and there is academic work on this. So I'm sure there's government prototypes for doing quantum key exchange, right? And solving some of these problems that way. To your earlier question, will it be quantum encryption that battles quantum decryption? I think it'll become another tool in the toolbox, right? And I think at some point, the big tech companies, people with a lot of resources will have quantum in their architecture if they don't already, securing some of their assets. Like we said, you can go rent one now and start playing with it and see how it works. Oh yeah, absolutely.
My next question is about global warming.
Okay.
Okay.
I'm feeling it here. These lights are hot.
Right now, Bitcoin is uses something like 0.4% of all the world's electricity.
Mm-hmm.
Do you see that going up or down with the advent of quantum computing?
Well, so the question is, can quantum solve global warming? And I
Not solve,
but help with.
my curiosity is, I really don't know about the internals of the quantum computers.
Mm-hmm.
How much electricity do they require?
Well, I know a lot of these have to be super cooled, and there's an awful lot of energy.
Not good.
There's an awful lot of energy in maintaining the entanglement, and there's an awful lot of work that's done in error correction. I mean, I think that's probably one of the biggest problems right now that they're trying to solve is having it be error tolerant and ideally be self-healing. They don't have those properties right now, where inevitably they destabilize after a certain amount of time and or adding more qubits. So once they solve that problem, I think they'll be off to the races with more and more and more qubits. But people don't know, right? There's theories for how they're going to do this, and there's a lot of work being done, but it might just be an impossible problem, right? That nobody can solve beyond a certain level of complexity. I think in terms of Bitcoin, you can already see things like Ethereum switching from proof of work to proof of stake, right? And it uses 95% or something less energy. So, that's solving the problem without even resorting to anything quantum. But yeah, I'm sure those quantum computers contribute to the climate like everything else. For the same size, I bet it's emitting more heat to maintain that really, really, really delicate state that it does. I saw your hand up first.
Initially, but you actually answered my question. Hypothetically speaking, even if they did do all the cleanup and screw up the error rates, it's still going to be producing like much more energy and actually emitting much more carbon anyway, regardless of the fact. So I see you already answered my question right there.
Yeah. So the comment was apparently they're using a lot more energy. I'd also, kind of look at history, right? In the 50s, computers took up whole rooms and used way more electricity than they do now for, much less, power or computing power. And these are the early days of quantum, right? At some point, you might have an Apple quantum watch, right? And if all these problems get solved, so I'm optimistic, but yes, sir.
So I apologize for asking you to speculate, but one interesting point that you raised is that governments and state actors in general will probably have access to more powerful quantum computers before the commercial.
Oh, sure.
things, right? So do you think it's possible that, for example, a government right now has the ability to break like AES 256 or something like that? Or how many years ahead of the commercial space do you think governments could be?
I'm
Thinking that-
totally speculating here. The question is, can governments do this now? Break AES, break other things. Asymmetric seems more vulnerable and everybody thinks that's going to happen sooner. So if they're able to break anything right now, my guess is it's asymmetric crypto. So they can, get through TLS, they can, get through PKI, they can, impersonate people if they want. But I guess my guess is they have to choose a very valuable target. I don't think they're just hoovering all that up and decrypting or breaking everything, right? There's probably some super high value message that they want to go after, some target they want to go after. But remember, usually it's the worst idea to go attack the cryptography head on. You almost always want to use a side channel attack. So for example, a really cool one that I liked, which doesn't use any quantum cryptography, is when you're using SSH, it's totally encrypted tunnel. It's hard to attack the SSH tunnel, but what they've proven that they can do is because every time you press a key, it transmits a byte or some number of bytes if it's Unicode. They know that in certain languages, certain combinations occur with certain speed, right? So, you can type the really quickly, whereas typing quixotic, right, is going to be a totally different combination. And they just use the timing and they can recover 70% of the message in some cases. So usually you don't want to attack the crypto head on. You want to install something on the machine. You want to go after a weak password. You want to do social engineering. It's really kind of a last resort to go actually try to first reduce the problem space to something that requires a lot of processing power, but now you can still do it. That's an expensive undertaking. So my guess would be if anything is going to fall first, it'll be the asymmetric crypto, and I think AES is going to be winnowed down and winnowed down. You're kind of stuck at 256. It won't do anymore. There are people that chain, AES on top of AES, but now that's a lot slower, and it's not like you got to 512, right? You got to something, in the upper 300s by doing something like that. Is AES safe for a little while? Probably. But it'll make the news when anyone other than the NSA or China or someone else breaks it, right? It'll be they're going to keep it a secret as long as they can, as long as they're able to do it, because it's very valuable then.
Any other question?
All right. Well, thank you all.